So strain energy we'll discuss first for axial loading, then in case of torsion, and finally we'll discuss in the case of bending. So as far as the strain energy is considered, strain energy is same as equal to work done and is represented by U is 1 by 2 force multiplied by dl, and we have dl is same as the deformation that equal to F multiplied by L divided by area divided by Young modulus. So if I replace dl, I will get the strain energy U is equal to 1 by 2 F multiplied by F into L by AE. So that is we have strain energy U is same as equal to 1 by 2. We have F square multiplied by L divided by AE. In the last equation, if I multiply the area in numerator, at the same time I will divide it by the area, then I will get the final expression in the form of volume. So we have strain energy is equal to 1 by 2 into F square. A into L is same as equal to volume divided by we have area square divided by Young modulus. So we'll use this equation to compute the strain energy in the case of axial loading. So strain energy, which is given as 1 by 2 F square into V divided by A square into Young modulus E, is used for constant cross-sectional area. But suppose we come across a non-uniform cross-section area, then we have to modify this equation. So let's consider here we have a bar BC and it has a variable area. Let's say here we have area at any distance x is equal to area A. So let us assume here that we have area is equal to A. Let's say from the fixed end, the given section at a distance equal to x, and it has a very small thickness that equal to dx. So this one is representing the thickness that equal to dx. So we can represent this thickness as dx. So it has a uniform cross section equal to A, thickness equal to dx. So we can replace here the volume V for the element. So we have dV will be same as equal to the area A multiplied by dx. And for this element, we can calculate the strain energy stored du as F square multiplied by dV divided by 2 times of A square divided by Young modulus. If I replace here dV as a constant area A multiplied by dx, then we can calculate here the total strain energy. So total strain energy is same as equal to U. You have to compute this value in the form of integral. We have F square multiplied by area A multiplied by dx. A into dx is same as dV divided by 2 times of A square divided by Young modulus. Since integration is done here with respect to x, we have to put the limit of x here, lower limit equal to 0, upper limit equal to L. So you have to develop here the relation for area in terms of x. One of the area term is get cancelled here, and we can calculate the strain energy U. So we have strain energy U is given as integral from 0 to L of F square into dx divided by 2 times of area multiplied by E. So suppose we have a uniform cross section of a rod and we have subjected the equal forces and opposite forces at the end of magnitude equal to F. Since here the value of the forces remain constant at any section, area is constant, Young modulus is constant. So we have total strain energy U will be equal to F square divided by 2 times of cross section area divided by Young modulus E. Integral of dx is same as equal to x, upper limit is L. So we have L minus 0. So in this case we have strain energy is same as equal to F square L divided by 2 times of A. Your force is compressive or the tensile, it doesn't matter because this one is a square term. So strain energy, whether your force is positive or negative, is always a positive value. For compression, you have to use the negative value of F. Square of negative F is positive and the square of positive term is always positive. So the strain energy is always a positive term. So So to calculate the strain energy, if you are given the value of force, you can use this equation. And if you have given the value of the stress, then the slight adjustment you have to do in this case. What we'll do here, we'll slightly readjust this term. We have F square. So additionally, we'll divide it here by A square. It means that we have one extra term, A will come. So immediately we'll cancel it. Multiplied by L divided by 2 times of Young modulus. So F square divided by A square is nothing but stress. So strain energy you can calculate in the form of stress as 1 by 2 normal stress square. A into L is same as volume divided by V of Young modulus. So if you are having the value of the force, you can use the first equation, and if you are knowing the value of the stress, you can use the second equation. The strain energy in a composite bar is calculated in the same fashion that we have done for single bar. Consider here that we have two bar. Let's say bar A has the area equal to A1, length equal to L1, Young modulus equal to E1, and the bar B which has area equal to A2, length equal to L2, and the Young modulus equal to E2, and is subjected to one centroidal force is equal to F. Now since here only one force is acting, the force for A as well as force for B is remain same. So in this case F1 is same as equal to F, F2 is also equal to F. So total strain energy in this case you can calculate by principle of virtual work. The total strain energy is consist of the strain energy of part A plus strain energy of B. And since here the force is same, so it is better to use this equation. So we have F square is common divided by 2 is common. So what is left in the first case is L1 divided by A1 divided by E1 plus L2 divided by A2 divided by E2. In this fashion we can calculate the strain energy in a composite bar. Now suppose we have given here the two composite bar A and B having their area, length, Young modulus is given as A1, L1, E1, A2, L2, E2, and we have three pointed force are acting as shown in figure. Let's say we have force is equal to P force, then we have force is equal to Q, and the force is equal to R. These forces are such that the stress in the segment A will be same as equal to sigma, and the stress in the second segment, that is sigma 2, is also equal to sigma. It means that both the part are subjected to the same stress value. If they have a same stress value, very quickly we can calculate here the stress by using the second formula. So we have total strain energy equal to the strain energy in the A plus we have strain energy in B. This time the stress is same for both A and B. So in that case we can take out here sigma square common divided by 2 into V1. V1 is same as a product of A1 into L1 divided by Young modulus E1 plus V2 is A2 multiplied by L2 divided by Young modulus of second rod, that is E2. Now consider the example here of a two bar here, bar 1 and bar 2. Both the bar has the same cross section area. The first bar has a length equal to L, second bar also has a length equal to L, and the first bar has a Young modulus equal to 3 times of E, second bar has a Young modulus equal to E. And we have given here the point force acting at section C is equal to F, which one is rightward. At B3 we have 3F is acting in the leftward direction, and we have fixed support where we have reaction equal to RA. Either you can draw here the force diagram to identify what is the force in section 2 and section 1, or you can cut the section at this point and apply the sigma fx and find out the force in the member 2 and the member 1. So we'll construct here the load diagram. Rightward force will take as a positive value and the leftward force will take it as a negative value. That is, positive will show above the reference level and negative will show the below the reference level. At point C here we have force is acting is equal to F, so we'll move vertically upward. So this one is same as equal to force F. Between C and B there is no force acting, so the magnitude of the load is remains same, that is equal to F. At point B here we have leftward force, leftward is negative, so that you have to show downward. So you have to move downward by magnitude of 3F. Already we have F here and again we have 2F here. So here finally we left here with minus 2F, and this force is remains same for AB. So in the member AB we have compressive force, and in the member BC we have tensile force. So in this case we have force F1 will be equal to minus 2 times of F. Force F2 will be equal to F. Area A1 and the area A2, they are identical, equal to A. Length L1 is equal to L2 is equal to L. And we have Young modulus E1 is equal to 3 times of Young modulus E, and we have E2 is equal to E. Since here we are knowing the force here, so it is better to use the first equation. So we have total strain energy U will be equal to U1 plus U2. Now the area is common, L is common. We will use this equation because we are knowing the force. So L can be taken common and 2 times of A can be taken common. So we have L divided by 2 times of area into F1. F1 is minus 2F, square of it will be 4F square, divided by Young modulus E1 is equal to 3 times of E, plus U2 is again F2. F2 is equal to F. So we have F square, divided by Young modulus equal to E. Now from this equation we can take out here F square common and even E common. So we are left here with F square multiplied by L divided by 2 times of area divided by Young modulus. We have 4 divided by 3 plus 1. 4 divided by 3 is same as 7 by 3. So finally we are getting this answer as 7, and here is 3 2, so it is 6. 7 by 6 F square multiplied by L and divided by AE. So this one is the total strain energy. A uniform steel rod with a diameter D equal to 30 mm and the length equal to 1.5 meter is subjected to an axial load P as shown in figure. The Young modulus of the steel is 200 gigapascal and SYT is equal to 250 megapascal. In the first part you have to calculate the minimum value of P at which the yielding will occur. That is the value you have to calculate corresponding to SYT. That is SYT multiplied by the area will be the minimum value at which the yielding will occur. Calculate the strain energy stored in the rod when the P reaches the yield point in the part A. Let here Py represents the yield load, then the value of Py will be same as the value of SYT multiplied by the area A. In this case we have SYT equal to 250 Newton per mm square. So area will take in mm square is pi by 4 into d square. We have d is equal to 30 square. So this answer will come in Newton, and dividing by 1000 you will get this answer close to 176.7 kilonewton. So this one is yield load. The strain energy at the yield corresponds to the modulus of resilience is given as total strain energy equal to 1 by 2. We have load is Py square multiplied by L divided by area and further divided by Young modulus. So we have 1 by 2. Load you have to take in Newton, that will be equal to 176.7 10 to the power 3. Length L is given as 1.5 meter. So if you use the units here as SI unit, your answer will be in joules. So this time I am preferring SI unit. Divided by area is pi divided by 4. 4 will shift in numerator. Diameter is 30 mm is 0.03 square. And the Young modulus is 200 gigapascal is 200 into 10 to the power 9. So this answer will directly come into Newton meter. So you get a strain energy is approximately equal to 165.7 Newton meter is same as joules. The step rod as shown in the figure is subjected to two equal axial loads of magnitude equal to P at section C and section T. Determine the total strain energy U. For BC rod, we have area is given as 2 times of A and the egg modulus equal to E, length equal to L. For CD rod, we have area equal to A, egg modulus equal to E and the length equal to L. So let's say here BC represents here the rod 1 and CD represents the rod 2. First of all, you have to calculate what is the net load in the CD as well as in BC. So apply here equilibrium condition. We'll cut the section here. So at point D here we have one force acting is equal to P. At C here we have one force acting is equal to P. This force we'll call as the reaction force is equal to F1, which one is internal force for the rod BC, that is labeled as 1. So if we apply the sigma Fx equal to 0 and the rightward force is positive, we have P is positive value, this P is also positive value minus F1 equal to 0. So force in the member 1 will be equal to 2 times of P. Another section plane will cut here for rod 2. Let's show the external force is equal to P and the internal force will be represented in the rod 2 will be equal to F2. So if we apply here sigma Fx, we will get the value of F2 is same as equal to P. The total strain energy U will be equal to U1 plus U2. That is we have 1 by 2 F1 square multiplied by L1 divided by A1 divided by E1 plus we have 1 by 2 F2 square L2 divided by A2 E2. Now the egg modulus is remain same, length is remain same, so that quantity we can take it outside. So we have 1 by 2, we have length is equal to L, egg modulus equal to E into F1 square is same as 2P square, so that will be equal to 4 times of P square, and we have A1 is equal to 2 times of A plus F2 square is same as P square divided by area A. So from here we can take out P square by A also common, so we'll get here P square divided by 2 times of E into A, L in numerator. 4 by 2 is same as equal to 2 plus 1. So finally we are getting the value of strain energy equal to 3 by 2 of P square into L divided by AE. The video you are watching is from the app, which is the Mohod class app available on Google Store. And in this app, we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.